Hello everyone and welcome back. My name is Mr. Cobalt and in this video I'm going to be going over the rates of chemical reactions. So let's get into this. So what do we mean by a rate of reaction? What we mean is that it is the number of moles of product that's formed per given liter of solution or per second, right? So it's an amount of product formed per time or per liter or per concentration, if you will. So that's what we mean. So here's kind of written out in a formula. So let's go to the previous, to the same example I used in my previous video where I have oxygen gas. So this is an atom, oxygen atoms in the gaseous form reacting with ozone to form two molecules of oxygen molecules. And so if I wanted to find the rate of this reaction, then I would measure the moles of oxygen molecules formed per liter per second. So that is how I would find the rate of the reaction. And so there are some factors that we need to keep in mind that are going to influence the rate of a reaction. So if we remind ourselves of what I talked about in my previous video on collision theory, we saw that there are two main things that there are two main factors that are going to need to be in place in order for a reaction to be successful. That is one, it's got to have this right amount of energy. It's got to have enough energy to overcome that activation energy to get over that hill. So that's the first thing. The reactants must collide together with enough energy to overcome that activation energy. And second, they have to be oriented in the right way. They can't just collide with each other any which way, willy-nilly. They have to be colliding together in the right orientations in order to form the right bonds and break the right bonds, to form that activated complex. So if they're not going to be oriented in the right way, then they're not going to form that activated complex. So when we think about factors that are going to affect reaction rates, then we want to think about factors that are going to affect those collisions or the rate at which they collide. So let's start talking about those factors. The first one I want to go over is temperature. So here we have temperature and rates of chemical reactions. Well, how is temperature going to affect the rate of a reaction? Well, if we increase temperature, for example, we got to go back to our collision theory and the idea of I'm blanking on the name, the kinetic molecular theory. So here we increase temperature. What happens to particles when you increase the temperature? Well, that's going to increase their average velocity as they're moving. So remember, temperature is a measure of the average speed or of molecules, or in other words, it's the measurement of the average kinetic energy of the molecules. So what is kinetic energy? If you remember, kinetic energy is equal to 1/2 times the mass of the particle times the velocity squared. So if you're going to increase the average velocity of the particles, then because kinetic energy is related to the square of the velocity, then that's also going to increase the average kinetic energy of the particles. If you increase the average velocity of the particles, that's going to increase the number of collisions between the reactants per second. So in a given amount of time, say 1 second, if you increase the speed of the particles, then you're going to increase the number of collisions you're going to have in that 1 second, in that given amount of time. Why? Because they're moving faster, right? Moving faster means they're going to collide more often in a given period of time. Well, what does that mean? If you're going to get an increase in the collisions per second, then also remember if you're increasing the kinetic energy. So the kinetic energy is increasing. What does that mean as far as the amount of energy needed to overcome that activation energy? Well, then you're going to have more molecules or more particles that are traveling with the minimum amount of energy that is needed to get them over that hump, to get them over the activation energy in order to form that activated complex. So you're going to have a larger fraction of particles that are going to collide between the reactants that are going to collide with the minimum needed energy to reach that activated complex. So here, increased average velocity means you're going to get an increased number of collisions per second. So you're increasing the number of collisions, but in addition to that, you're increasing the fraction of those collisions that are going to have the minimum energy necessary. So both of these then lead to an increased reaction rate. So remember that the increased reaction rate is related to the moles of formed product. If we have a greater fraction of collisions that have that minimum energy needed, you're going to increase product. More product is formed in a given amount of time because you're increasing the number of collisions as well. So all of this is to say that if you increase temperature, then you're going to increase the rate of the reaction. Okay, well, what about other conditions? Well, let's look at concentration. What happens if we increase the concentration or decrease the concentration? But before we go there, let me also say that this works in the opposite direction. Well, if I lower the temperature, then I'm going to lower the average velocity. I'm going to decrease the number of collisions per second, and I'm going to have a decreased rate of the reaction. Again, in this way, if you think about it in terms of energy, if I decrease the temperature, then I'm going to decrease the average kinetic energy. I'm going to decrease the fraction of collisions that have the minimum energy, and therefore I'm going to decrease the rate of the reaction. Okay, so now let's talk about concentration, shall we? Okay, so let's talk about concentration now. So concentration, how does concentration affect rates of chemical reactions? Well, if you think about it, what does concentration mean? You can think about concentration as being the number of particles in a particular space or a particular volume, if you will. So if I increase the concentration of something, then that means I am increasing the number of particles or things per unit volume. So for example, if I'm increasing the concentration of sugar in my soft drink or in my Kool-Aid, right? What do? I have a glass of the Kool-Aid. I just put in more sugar, right? I put in more Kool-Aid into the same volume. So that means I have a much more concentrated form of my Kool-Aid or my soft drink because now I have more particles in the same solution, in the same amount of the Kool-Aid or the soft drink that I have. So I haven't changed the volume, I just added more particles. So increasing the concentration means that you're increasing the number of particles in a given space or in a given solution or volume, right? So in this case, if we think of it that way, then if we start off with an increased concentration of reactant, that means we're increasing the number of particles per unit volume, okay? So if I cram more particles into the container or into the space, now I have more particles in there. What does that mean? That means I'm going to have a decreased average distance between the particles and decreased volume that's available in which to move without colliding. In simple terms, that means that there's less space to move around without colliding. which means that you're going to collide more often. So think about an example of if you have a crowded room, right? So if I have a classroom or say a gymnasium and I have 10 people walking around in the gymnasium, there's a whole lot of space. Oops. Sorry about that. So as I was saying, if I have a gymnasium and I have 10 people walking around in that gymnasium, I have a whole lot of space for them to walk into. And if they're blindfolded and they're just walking willy-nilly without seeing, of course, walking slowly, they can touch a wall and move in another direction. They can bump into each other eventually, but they're not really going to collide with each other all that often. But if I jam pack that gymnasium with 1,000 people walking around blindfolded, then there's less space to move around in, higher probability of bumping into someone more often. So you're going to have more collisions with more particles, like what's the word I'm looking for? Jam packed together, right? Squeezed together. So what is this going to do? It's going to increase the number of collisions between reactants per liter per second, right? So remember, per liter per second. And what effect is that going to have? That's going to increase the number of particles that fulfill the requirements for reaction, right? So if I have more particles bumping around, right, I have more likelihood of them bumping in the right orientation and bumping into each other or colliding with each other with the right amount of energy. So that's going to lead to an increased rate of reaction. This also works in terms of volume changes. So it's the same idea. Instead of packing in more particles into the constant volume, I can change the volume of the container, keep the particles the same. So if I took my gymnasium with 10 people and I squeezed it to the size of a closet, so I've now reduced the volume. The people that were in the gymnasium are now crammed into a closet, and so moving around, they're more likely to bump into each other a lot more often than they were in that gigantic space of the gymnasium. So changing the volume works in the same way. So if you take another example like your combustion engine of your car, right? The piston is moving up and down. When the piston moves in such a way to decrease the space where the gas and air are mixed, you're decreasing the volume. That means you're giving the space, the particles, you're pushing them closer together. There's less space to move around in. More collisions are available, and therefore the reaction speeds up. The reaction rate speeds up. Okay, so we've done temperature, we've done concentration. Next is the catalyst. How do catalysts affect rates of chemical reactions? Stay tuned. Okay, so let me explain first what a catalyst is, and we'll talk about how a catalyst affects reaction rates. And so here, the first thing we need to realize is that a catalyst is some substance that when you're adding it to the reaction, it causes the reaction to speed up, but itself is not used up in the reaction. It could be used to cause the reaction to speed up. First, to cause reactions to be more favorable to making product, to create more favorable collisions. But in the end, the catalyst itself is not used up during the process. So if the catalyst is used in the reaction, then it'll come back out of the reaction later on. So what do I mean by that? So here's an example. So if we go back to the example of ozone reacting with an atom of oxygen to form the two molecules of oxygen, we could do it this way here. So this is the one way, do it directly with no catalyst. So this will have a certain rate to it. But we could use in a second option, we can use a catalyst. So in this case, the catalyst would be the chlorine. So we have a chlorine atom, not a chlorine molecule. So a chlorine atom can collide with ozone molecule, and so that the chlorine atom can bond with one of the oxygens here to form ClO, and then that leaves O2 left behind. But then the ClO can further react with the atom oxygen, and so then this will form a bond between the two oxygens to form O2, and then that leaves your chlorine left. So you'll notice here that in this case, the chlorine is used, it combines with an oxygen here. Now it's ClO, so the catalyst is gone, but then the ClO is used here to then cause the oxygen here to react with this oxygen to form another O2, and you get the ClO back. So here it's used, and here you get it back. So overall, it's not used at all. So then when you combine these two equations, the overall equation is this: O3 ozone, right? So we have ozone reacting with O, right? These two cancel out because I have this on both sides. These two cancel out, and I'm left with two oxygen molecules on the product side. And so we have Cl over the arrow to indicate that Cl is the catalyst being used in this reaction. And so if you're using the catalyst chlorine, then there's two steps to this reaction. And these two steps happen much more quickly because the catalyst lowers the activation energy of the process. So this gives a different process, or a given, how should I say, way of forming the products different from this right here. So there's a different chemical pathway for these two such that the activation energy is lowered, and therefore it's much easier to overcome that activation energy barrier, form your activated complex, and form the products compared to this. Okay, so the next thing I want to show you is the energy diagrams for both of these so you can see what I'm talking about. So stay tuned. Okay, let's look at the energy diagrams for each of these two possibilities. So what I have here is the energy diagram of the uncatalyzed version overlapping with the catalyzed version. So here's where our reactants are. If we ignore Cl, that's our catalyst. So without the catalyst, we're looking at oxygen and ozone reacting together. And so they're going to react. The uncatalyzed would be this one right here. So uncatalyzed reaction is the orange. So that would go up. So the oxygen atom will collide with the ozone, and then you're going to get your activated complex. So so you can see the activation energy here. So if I draw this across, then you'll see that this is the activation energy needed for this pathway here. And so you got to raise the energy this much to get to the activated complex here. And then once you get here, then this bond will break and this bond will form, lowering the energy, and then you end up with two oxygen molecules. So this is the uncatalyzed pathway. But look at the catalyzed pathway. So here, if we include the chlorine here, then the three of these react together. And notice here, if I bring this across, you'll see here how much lower the activation energy is using the catalyst. So here you only need to go up this far. So the chlorine atom reacts with the ozone here. So then just like you have the activated complex here with oxygen, here you have chlorine starting to form a bond with one of the oxygens of ozone, and then the oxygen bond here is breaking here. So you've got the activated complex. This activated complex doesn't require as much energy, so it's a lower activation energy, and so this is going to go a lot quicker and a lot more easily. You're going to have more molecules or more reactant particles with this amount of energy that are going to be able to collide and go to the next step. So then this is your activated complex. It goes down to this level here. So now you've got the CLO. So you've got this form, and this bond breaks, and you're left with O2. So there's your O2. And then at this step here along the pathway, you have your O atom. This is now going to react with this, forming the complex. So your oxygen, your single atom oxygen, is going to collide with CLO, and then you've got this activated complex here. And again, here's the activation energy that needs to be overcome, so relatively small. And so this bond is starting to break, and this bond is starting to form. And so you reach activated complex, and then it goes downhill and forms your O2, your two O2 molecules, and leaves the chlorine left to keep going with another reaction. So you can see here that one, the activation energy is much smaller going this way with the catalyst. Also, you can see that there's another pathway. So the catalyst provides an alternative pathway to get to the products, and that pathway allows less energy to be needed for the reaction to occur. So this is going to make the reaction go a lot more quickly. Okay, so that's it for catalysts. So let's finish up with the summary about catalysts. So I'll be right back. Okay, so let's summarize what I said about catalysts. So first, the catalyst provides an alternative pathway with a lower activation energy. We saw that with the energy diagram. So what does that mean? What that means is that because the energy activation energy is lower, the bar is lower, so a greater fraction of collisions between the reactant molecules are going to have that amount of energy. The lower the bar, the more people who are going to have the ability to jump over it, right? So if you lower the activation energy, then a greater fraction of the molecules that collide, they're going to have that amount of energy that's going to allow them to form product. So therefore, a greater fraction of the collisions will lead to the products. Therefore, you have an increased rate of the reaction. So that is, in a nutshell, how catalysts lead to the increased rate of the reaction. Okay, so now to finish up with catalysts, we need to talk about the distinction between homogeneous catalysts and heterogeneous catalysts or heterogeneous catalysts. So stay tuned. Okay, finally, let's talk about homogeneous catalysts versus heterogeneous catalysts. So the difference between these two catalysts is whether or not the catalyst is in the same state as the reactants. So for a homogeneous catalyst, if we remember homogeneous, homo means same, geneous means kind, so same kind. So homogeneous catalyst is a catalyst that is in the same state as the reactant. So the catalyst and the reactants are in the same state, so homogeneous. So an example of that is the example we just went over. Here we have oxygen and the ozone in the gaseous state, and our catalyst chlorine is also in the gaseous state. So this is an example of homogeneous catalysis, where we're using a catalyst that is in the same state as the reactants. A heterogeneous catalyst, if you remember, hetero means different. Again, geneous means refers to kind, so different kind. So here we have a catalyst that is not in the same state as the reactants. So the reactants and the catalysts differ in the state that they're in. An example of this is the catalytic converter on your car or your automobile. So the catalytic converter is made up of a solid mixture of transition metals and metal oxides. So this is a solid, it has a solid surface, and this is where the exhaust is coming through. All of the products from the combustion engine is going to go through the catalytic converter, and this is where things like NO gas or NO2 gas is going to be catalyzed into other things. So in the catalytic converter, in the metal of the catalytic converter, you have transition elements like platinum, palladium, iridium, and rhodium. So these are going to help catalyze the reactions to the gases that are coming through your exhaust. And so because the catalytic converter is a solid and the reactants that are reacting are gases, this would be an example of a heterogeneous catalyst. And so that's it for this video. I hope you enjoyed the video. If this was helpful in any way, if you learned something from this video, then please by all means like the video, share the video, hit that like button. Also, make sure that you subscribe to my channel, hit that notification bell. When you do, make sure you click all so you can be notified by all the videos I put out. And then finally, put a comment down below in the comment section. Let me know what you think. Ask me questions. I would love to hear from you. If you have a topic you want me to cover, if you have a question or a problem you want me to help you with, put that down below in the comment section. I would love to do that for you. Thanks for joining me and have a great day.